Hey everybody, welcome back. This is Chem 103 lecture. We are completing chapter 8, so this is chapter 8 part 2. If you did not watch part 1, where we introduced the mole, you should do that first, because we're going to continue our conversation about the mole like you know what it is. If you are a little bit shaky on the concept of the mole, rewatch the first part, maybe take a look at your notes, and then get ready for this. We're going to start off with percent composition. Percent composition of a compound lists the mass percent of each element. So what you'll need to do is, for the percent, you take the number of atoms of an element that are in the compound, you multiply that by the mass on the periodic table. But you express that atomic mass in grams. You divide that by the molar mass of the compound. Once you have that, you multiply it all by 100%. So I'll give you an example. Let's say we want to find the percent composition of water. Water is H2O. For the molar mass, we've got 2 waters and we've got 1 oxygen. Now that we have the molar mass, we can figure out our percentages for each element. For the percent hydrogen, we write out the number of hydrogen atoms that are in the compound. And there are 2 atoms of hydrogen in water. We multiply that by the atomic mass of hydrogen. Depending on the periodic table you use, it might say 1.01. You might have one that has another decimal place. Either way, you'll get pretty much the same answer. So there's the number of atoms times the atomic mass of hydrogen in grams. We divide that by the molar mass of water. And then multiply by 100%. When you do that, you should get somewhere in the ballpark of 11.2%. Now let's calculate it for oxygen. There's only 1 oxygen in water. If you look at the periodic table, it'll say 15.999. It might say 16.00. Depends, again, on how many decimal places there are on your periodic table. You divide that by the molar mass of water and multiply by 100%. You should get somewhere in the ballpark of 88.8%. Now, since these are percentages, it should always add up to 100%. So remember that. You can check your work that way to make sure that you did it right, that everything adds up to about 100%. It could be 100.1 or something like that because of rounding. That's okay. But you shouldn't get 115%. That's wrong and you should recheck your math. Here's an example. I encourage you to pause the video here and try it out. This is the molecular formula for TNT. First, calculate the molar mass, and then try to figure out the percent composition for carbon, hydrogen, nitrogen, and oxygen. Here we go. I'm going to do the molar mass calculation in red. So let's see what we've got here. We've got carbon, and there are 7 of them. The atomic mass on the periodic table for carbon is 12.01. And that takes care of the carbon. Okay, that's the C7 part. Then we've got 5 hydrogens. Then we have 3 NO2s. So 3 times nitrogen and the 2 oxygens. So all of this together is this portion. When you add all that up, you should get 227.125 grams. So that's how many grams there are in 1 mole of TNT. Now we have to do the percent composition, which means what percentage does each element have in terms of the mass of a mole of this stuff. For the percentage of carbon, well, we've got 7 carbons. The mass from the periodic table is 12.01. You divide all that by the molar mass of TNT, multiplied by 100%. And we continue doing this for each one of the elements. I'm going to alternate colors here so that it's a little bit easier to see. Next, we'll do hydrogen. We've got the number of hydrogens times the mass of hydrogen. Divide that by the molar mass of the entire compound. Multiply by 100%. Next, we'll tackle the oxygen. There's a total of 6 oxygens. Remember, 3 times 2. There's the percentage of oxygen. Now we need to tackle the nitrogen. There are 3 nitrogens because, again, we have this 3 out here. And there are all the percentages. This is our percent composition for TNT. As I said on the last slide, make sure that you double check, add up your answers, make sure that they add up to roughly 100%. If it's, 100.1 or 101%, that's fine. It shouldn't be 75%. It shouldn't be 110%. It should be very close to 100%. Next topic is empirical formulas. The empirical formula of a compound is the simplest whole number ratio of ions in a formula unit, or atoms of each element in a molecule. The key that you want to remember here is simplest whole number ratio. So if we have benzene, its molecular formula is C6H6. In the chemical benzene, there are 6 carbons and 6 hydrogens. The empirical formula of benzene is CH, 1 carbon and 1 hydrogen. That's the simplest whole number ratio of atoms of each element, 1 to 1. The molecular formula of octane is C8H18. The empirical formula, if you reduce that down, is C4H9. We can't reduce that down anymore. We're going to learn how to figure out the empirical formula of a compound giving mass information or percent composition. So let's calculate an empirical formula. This is just one of the styles of problem that you may see when it comes to calculating the empirical formula. You're given the number of grams of reactants and products, some combination thereof, and you have to do some sleuthing and figure out what the empirical formula is. Here we have a sample of radium metal that's heated to produce 1.755 grams of radium oxide. And we need to figure out what is the empirical formula. Here are the 2 bits of information that we have. Now let's put them together. We have radium metal, and it was heated to produce some kind of radium oxide. I'm putting the X and the Y as subscripts because I don't know how many radiums and how many oxygens I have in this compound. So those are placeholders. That's what we're figuring out. What we also know from the problem is how much of the radium metal we have, 1.640 grams. And we also know how much radium oxide we produce. Now that oxygen doesn't come from nowhere. There's oxygen in the air. So obviously the radium must have reacted with oxygen gas. Remember that we can't just create or destroy matter. So there had to be oxygen in the presence of this metal that was heated. Because of the law of the conservation of mass, which we've talked about a couple of times, the mass of the reactants must equal the mass of the products. So if we take the amount of product we make and subtract the amount of reactant we have, then we can figure out how much oxygen gas reacted. When you do that, you figure out that you reacted with 0.115 grams of oxygen gas. The first thing we want to do here is calculate how many moles of each reactant we have. For the radium, we take the 1.640 grams and we multiply by a unit factor that has 1 mole of radium and the molar mass of radium, which we get from the periodic table. So that's how many moles of radium reacted. We have to do the same thing for the oxygen. We want to figure out how many moles of oxygen, not oxygen gas, but just the element oxygen. So that tells us the number of moles of each reactant we have. The next step is to figure out the ratio between the reactants. That is a mole ratio, which we call N. We only have 2 elements here. So what we do to calculate the N is to take the smallest number of moles, put that down in the denominator. Take the larger number of moles, put that in the numerator. When you divide these two, you get approximately 1. What that 1 means is that you have 1 mole of radium for every 1 mole of oxygen. So our empirical formula is RaO. But what if you don't have a ratio that's just 1 mole to 1 mole? I'll show you that in the next example. This time, we have the same style of problem, but, spoiler alert, we're not going to have a 1-to-1 ratio at the end. So here's what you do for that. We do the same thing as before. We use the law of the conservation of mass to calculate how many grams of each reactant we have. In this problem, we have a sample of cobalt, and it was heated with excess sulfur. And we make cobalt sulfide. But cobalt is a transition metal. It can form multiple ions. We don't know what the ratio of cobalt to sulfur is. So notice there is no parentheses with the Roman numeral like we normally would have for something like this. That's because we don't know it yet. We'll do the same thing where we kind of write out a crude reaction. We've got some cobalt metal reacting with sulfur. It's heated, and we make some kind of cobalt sulfide. We don't know how many cobalts there are for every one sulfur. That's what we're figuring out. Also from the problem, we know how many grams of cobalt, and we know how many grams of product. But we do not know how much sulfur reacted. We can figure that out though. The mass of the reactants should equal the mass of the products. You subtract the 1.15 grams from the amount of product we make, and that tells you how many grams of sulfur reacted. Now that we have all of our information, we are first going to calculate the moles of each reactant. To convert, we need the molar mass of sulfur and the molar mass of cobalt. We're starting with sulfur. 1 mole of sulfur has a molar mass of 32.066 grams. That's directly from the periodic table. We do the same thing with the cobalt. In 1 mole of cobalt, you look at the periodic table, you find 58.93 grams, and that's how many grams are in 1 mole of cobalt. Now we've figured out the number of moles. Our second step is to figure out what our mole ratio is. Remember that we call that N. And since there are only 2 elements here, it's the mole ratio between cobalt and sulfur. Put the smaller number of moles on the bottom. In this case, that's the number of moles of cobalt. You put the larger number on top. When you do that, you get about 1.5. But we can't say 1 cobalt and 1.5 sulfurs. We can't have half of an atom. The empirical formula has to have the simplest whole number ratio. 1.5 is not a whole number. What does that 1.5 mean? It means you have 1.5 moles of sulfur for every 1 mole of cobalt. We need to figure out a way to have 2 whole numbers here. Well, if you multiply them both by 2, then you get 3 moles of sulfur for every 2 moles of cobalt. Those are whole numbers. And these whole numbers translate into the subscripts for our formula. And that's our empirical formula. Now you may run into problems where you have more than just 2 elements. We'll do those in class. So that is an incentive to come to class because you absolutely have some of those in your homework. Come to class, we'll do some practice with compounds that have more than 2 elements, and you'll be good to go. There's another way that you can calculate empirical formulas, and that's from mass composition. Acetylene is 92.2% carbon and 7.83% hydrogen. It's also incredibly flammable, and it's used for pipe soldering, like melting, copper pipes. If you're trying to put together a long length of copper, like you're maybe under someone's house doing some plumbing, that's what acetylene can be used for. I personally don't want any parts of it. We can figure out the empirical formula of acetylene simply by using the mass composition. It's even simpler here because we don't have to do any kind of math to figure out how many grams of this or that are reacting. All we have to do is make an assumption. A percentage adds up to 100%. We use that to our advantage and assume that we have 100 grams of acetylene. And whenever we're given the mass composition, or we can calculate the mass composition, we can make this assumption and do some math. If I have 100 grams of acetylene, then that means if it's 92.2% carbon, in 100 grams, I've got 92.2 grams of carbon. And I can take those grams and convert to moles. So our first step is the same. We're calculating the number of moles from the mass, but the mass isn't explicitly given in the problem. We make an assumption that we have 100 grams of the substance, and therefore we can take those percentages and write grams instead. So that was our first step. Our second step is again calculating that mole ratio. You put the smallest amount of moles in the bottom, and then you put the carbon on top. That's about 1 to 1. Oh, I wrote that in the reverse. .68 is usually smaller than 7.77. And you get about 1. It's not exactly 1, but it is pretty close. That 1 means that you have 1 mole of hydrogen for every 1 mole of carbon. For our empirical formula, it's CH. These numbers, whether they're 1 or whatever they are, they're the subscripts. Since we don't usually write 1 as a subscript, you leave it out. We can calculate molecular formulas as well as empirical formulas. The molecular formula is the actual formula of the compound, and it's a multiple of the empirical formula. What we need to figure that out is simply the molar mass. We figured out the empirical formula of acetylene is CH. If we're told that it has a molar mass of 26 grams per mole, then we can figure out what the N is. And in this case, the N tells us the multiple of the empirical formula. This is how you calculate that. You take the molar mass of your compound, aka the molecular formula, and you divide it by the molar mass of the empirical formula. To figure out the molecular formula of acetylene, we first have to calculate the molar mass of the empirical formula. Our empirical formula is CH. I abbreviate molar mass MM. Carbon is 12.01 grams. Hydrogen is 1.008 grams. When you add that together, you get 13.018 grams, which is pretty much 13. The molar mass of our compound, which is the molecular formula, is 26 grams per mole. What we have is 13.018 grams. That's about 2. So this tells us how many times we're multiplying our empirical formula by. Since our empirical formula was CH, we need 2 of them. That's our molecular formula. We can put all of this together and use the percent composition of a compound to first figure out the empirical formula. And if we're given the approximate molar mass of the compound, we can also figure out the molecular formula. We've got an insecticide that causes dizziness in humans. We also have the percent composition for this compound, along with its approximate molar mass. Those are all of the important bits. You see all those words in that paragraph. But the important things, percent composition and the molar mass. That's why I always highlight or underline or simply rewrite the information that I'm given so that I'm not overwhelmed by all the other stuff that may be in the word problem. The first step is always to calculate moles. We're calculating the number of moles of each element. To do that, we have to assume that we have 100 grams of whatever substance we're starting with. That means that the percentages we see, like 24.8% carbon, we can say that's not percentage, that's grams. When we have 100 grams, that's absolutely what it would be. We use the molar mass of carbon to figure out how many moles. We go through and do this for every single element. Thankfully, there's only 3. Now, normally we'd be done, but we have 3 elements in this compound. There's no limit to how many elements you can have. Remember that we're getting these molar masses from the periodic table. Nothing fancy here. Now, all of these are about the same, 2.06, 2.08. That's about 2 moles of each compound. But I want to show you what we would do if one of them wasn't the same. So I'll show you how we go through and figure out the ratios. Let's calculate the mole ratio of the empirical formula. The smallest number of moles that we have is 2.06. And both the carbon and the chlorine, there's 2.06 moles of each of these elements. We'll just stick with putting the carbon in the bottom. Then you take each of the other elements and they have a term as the numerator. So the first one we're going to use is the hydrogen. And this is going to tell us the number of moles of hydrogen for every 1 mole of carbon. When you do that math, it's 1. So the ratio of hydrogen to carbon, there's only 1 mole of hydrogen for every 1 mole of carbon. Then we do the same thing with the chlorine. When we do this division, it tells us how many moles of chlorine are in the empirical formula for every 1 mole of carbon. It just so happens that the answer is 1. So our empirical formula is CHCl because all of these have 1. And these are our subscripts. There's a third step this time, and that is to determine the molecular formula. We calculate the molar mass of the empirical formula. Then we take the molar mass of the compound, which we're given in the problem, and divide that by the molar mass of our empirical formula. When you do that math, it comes out to about 6. When you do this math, it should be fairly close to a whole number. What that means is that we're taking our empirical formula and multiplying it by 6. And that's our molecular formula. We will do practice with these in class as well, and they'll be a little bit more complicated than 1-to-1-to-1. But this is the same method that you do. We'll practice, and we'll make sure that you do well on your homework. So come to class. It's important this week. That's all I have for you. Thanks for watching. Make sure you tune into the live lecture for practice problems and details regarding assignments and exams. As always, please stay safe.